Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. In the last session, we discussed the neutral satellite environment, that is the spacecrafts it is exposed to or it behaves in a neutral environment. So, what are those neutral particles or gas particles? We discussed those and we discussed what are the effects of the neutral space environment. So, we have seen that those neutral particles, it is dominated mainly by the atomic oxygen, and we discussed how this atomic oxygens are generated in higher altitude or higher altitude atmosphere. This is mainly because of the photo dissociation, basically at the height of 90 to 600 kilometers this happens, and the intensity of is maximum at 400 kilometers. We also discussed what are the factors on which this atomic oxygen intensity depends. So, those things we discussed in the last class. Along with that thing, we discussed what are the effects of the atomic oxygen attack or AO attack on the spacecraft. So, basically we have seen because that the atomic oxygens are highly reactive. So, they oxidizes the surface or there is the chemical reaction, and as a result of the chemical reaction there is surface erosion, then the contamination along with the like the effects like the outgassing which happens in the vacuum environment, outgassing of the surfaces of the spacecraft bodies along with the UV radiation plus this atomic oxygen. This three that makes a permanent contamination layers or it is a very stable contamination layers on sensitive surfaces like the glasses of the camera system, or it can be very sensitive thermal control system. We have seen another effect of the atomic oxygen. This is the spacecraft glow because of the high energy imparted. There is the eruption of the gas particles near the surface, near the especially in the spacecraft in the REM surfaces. Those things emits the light at different wavelengths, and it shows it is glowing. So, this can be shown when the sunlight is not there, that at night you can see this type of the glow in the space shuttles. So, yesterday we discussed that one also. So, today we will be discussing the other effect, that is called the drag force on the spacecraft. It is also called the atmospheric drag. So, we will discuss what are the drag force, what are the factors which on which the drag force is dependent, then how this drag force changes the satellite orbital parameters, mainly the its altitude as well as the period. Okay. Now, why this atmospheric drag is there? So, because of the density of the neutral gas is the primary atmospheric property that affects the spacecraft orbital altitude, lifetime and motion. So, these are the three things it happens because of this atmospheric drag. Of course, in low earth orbit this electrically neutral atmosphere density primarily dominated by the atomic oxygen is too tenuous. So, the density is very low to support the human life, but it is sufficient, it has the sufficient density to cause significant interactions with the spacecraft moving at an orbital velocity of 8 kilometer per second. So, this again it depends on this orbital velocity, what is the altitude. So, when you consider this low earth orbit, it average it can be 8 kilometer per second. Whenever you go higher and higher altitude, this orbital velocity will reduce. Now, the impact of atoms at this high speeds will give rise to an aerodynamic drag force, which may also, this is also another effect, which may physically sputter material from some of the surfaces, because this spacecraft is moving at a very high speed and the particles are also moving. So, in because they are having very high kinetic energy. So, the interaction or this of this moving particles with the high speed spacecraft it can give rise to the sputtering of material from a few surfaces. So, a drag force on the as I already said that happens in the low earth orbit. So, basically we this is considered only that is orbits up to 1000 kilometers square, which we call the low earth orbits. So, what happens, a spacecraft in the low earth orbit, if it is not corrected by the attitude and orbit control system, because of this atmospheric drag, it will do deorbit, means its altitude, that is orbital altitude will decrease or decay, and subsequently it will re-enter into atmosphere and the spacecraft will get burnt. Another effect, so this is one is the that is the decay of its orbit or the deorbiting. The other effects is that the density effects directly, this effects of that it contribute to the torques experienced by the spacecraft due to the aerodynamic interaction between the spacecraft and the atmosphere. So, what happens because of this torque, the satellite orientation gets changed, or it is called the attitude, means whatever the satellites, the axis is that yaw, pitch and roll axis. So, yaw axis should ideally it should point to the center of the earth, but because of the torque it may deorbit. In that case, what will happen, the whatever the satellite link is there, whatever the communication system is there, the wireless communication system, they will be out of line of sight. In that case, the satellite cannot be operated. So, all these things are corrected, as you already have seen in the satellite segments, that is attitude and orbit control system. So, in attitude and orbit control system, the satellite's orientation as well as its orbit is called the station keeping. These things are done. Okay. Now, what is that aerodynamic force? Now, let us see its the mathematical treatment. So, aerodynamic force is the force created by the spacecraft's movement through a neutral density atmosphere, and this force, this is the force which results from the momentum exchange between the atmosphere and the spacecraft. So, that can be decomposed into three forces, namely the lift, drag and side slip. So, this you can see from this diagram. So, the spacecraft is moving in this direction. So, the drag force will be opposite to that, as if it is trying to decrease its velocity. Now, another force it is perpendicular to this drag force, it is the lift, this is called the lift, and perpendicular to both these forces, this is the drag force and the lift force, the third force is called the side slip. Now, these two forces, that is the drag force and the that is the lift, these two are they lie on the orbital plane. So, in the orbital plane orthogonal and parallel to the velocity vector. So, they are parallel to the velocity vector, whereas the side slip is orthogonal to the orbital plane. So, this will be clear when I see. Yeah. So, you can see this is the earth and the satellite is orbiting. So, this is this will be the velocity direction, satellite is moving in this direction. So, drag force will be the opposite. Okay. Now, this is this force. So, this is again these two are in the x plane. So, this is the lift force, and the perpendicular to this two forces as well as perpendicular to the orbital plane, which is also in the direction of the angular momentum. So, this jet, so this is the side slip. So, these components of this aerodynamic force on a satellite are represented by these expressions. So, it is F I as equal to half rho A C I B square. So, we will see what are these parameters. So, A it is a representative area of the moving body, or here the spacecraft. So, this in this expression it is expressed in meter square. Then C I is the coefficient, it is called the coefficient of drag. Sorry, I will not name it right now the drag or anything. So, we will write it just a coefficient. Then this F I is the force force is, it is in Newton, then the I here, now we will define I as d. So, d is the drag, L is the lift and S is the side slip, and V is the spacecraft velocity with respect to the atmosphere, and it is meter per second, and rho is the atmospheric density, that is expressed in kg per meter cube. Now, at the altitudes of the most of the spacecraft, the total aerodynamic force is small and is primarily opposed to the velocity vector. So, that except for re-entry studies, only the drag force is generally assumed to be present. So, only we will consider in our subsequent slide, we will not consider the lift as well as the side slip, but we will only consider this drag component. So, we will consider only the FD part, that is the drag force. Okay. So, the effect of the drag on the period. So, we will see the that is the period means it is the time taken by the satellite to complete one revolution around the earth in a particular orbit. So, that is called the orbital period, and what is its effect on the semi major axis of the spacecraft in a circular orbit, but we will show it circular as well as elliptical also, in a circular or elliptical. So, how can we find that? So, the time rate of change of the energy of a spacecraft is equal to the time rate of change of the work of the drag force. So, this is the energy. So, energy I can write E is equal to force into this force vector into displacement vector. Suppose this is that. Okay. So, basically it is f dx of cos of theta, where it is the direction of the theta is the angle between the direction of the force as well as the, that is the displacement vector, that is the dx direction. Okay. Now, here what is happening, I am taking the derivative of this with respect to time. So, here this x, so dx will I will write it x, or I can write it r, that is better I write in terms of r. So, now the b will be dr by dt. So, I can write d by dt is equal to f dot b. So, I can write here f dot dr by dt or f dot b. Now, the drag force and the velocity vector, they are in the opposite direction. So, if the drag spacecraft is moving in the direction, drag force is anti-parallel. So, their dot product will give me, this is the cos of pi will be minus 1. So, that is why I get this. So, substituting this expression for the drag force, what we have written in this earlier slide. So, here is the f is the aerodynamic force vector and b is the velocity vector, and d by dt, actually it is d by dt, it is the rate of change of total energy of the spacecraft. This is in watt. So, now we can write the energy of the spacecraft in terms of the semi major axis like this. So, how I can write that? So, we know that is the total energy of a spacecraft in orbit, it is given by this expression. So, this comes from E is equal to it is the summation of the potential energy as well as the kinetic energy, and it is very easy to show that the potential energy is given by mu into m divided by A, whereas the potential energy is given by mu, sorry, this is the potential energy and the kinetic energy is given by mu m divided by twice. So, you get basically this when you sum this two, and where mu is equal to, so your P is equal to mu m by A minus and K E is equal to mu m by twice A. So, you get this value. So, now I can substitute this value d I by dt using this previous expression. So, now I can put d dt is equal to this expression mu m by twice a square d A by dt, and now this is equal to this the drag force. So, now I can express this d A by dt by taking this to this side. So, I can write this expression like that. Now, again here the velocity of any spacecraft is given by this expression that already we have seen. So, this is that is the altitude at any time, that is the r. So, it is given by mu by r to the square root of mu by r. So, I can substitute this here and we can get the expression for the dA by dt. The A by dt means the rate of change of this semi major axis with respect to time. Okay. So, here again A is the semi major axis and it is in meter, E is the total energy and m is the mass of the satellite and r is the spacecraft, or you can say it is spacecraft altitude. And t is the time. So, here we are able to do the derivation, because here the semi major axis is a function of time. Because of that atmosphere drag, this altitude or the semi major axis of the satellite is changing with time. So, that is why you are able to differentiate it with respect to time. Okay. So, this is the gravitational constant of the primary body that already we have seen. So, now this expression we have derived. So, now if we have a circular orbit when r is equal to a. So, whatever may be the circuit, the satellite is there, its altitude is a. So, I can substitute here r is equal to a. So, if I substitute here r is equal to a, then I get this expression. So, this gives me an important expression for, that is how the rate of the change of the radius or the altitude of a satellite in circular orbit, it changes with time. So, you see this is a function of, that is what is the air density, what is the effective area, what is the drag coefficient and what is the mass of the satellite, as well as this gravitational factor. Okay. Now, the orbital period is given by tau is equal to, so this also you have seen, this is the time taken by a satellite to complete one revolution. So, this is given by this expression. Now, if I differentiate it d tau by dt, then I will be able to write this twice pi, then it will become a cube. So, it is a, so it is a 3 by 2 minus 1 divided by 3 by 2 minus 1, and then this square root of mu will come out, and then I will have a d by dt. So, now I can put this di by dt where tau is the period s. Now, already we have this expression da by dt. So, I can substitute this expression here and I can get, this is the rate of the change of the time period with respect to time, and finally, I get this expression. Again here when r will be equal to a, I have this, when a circular orbit it will be r is equal to a. So, I get this is the expression for. So, these are the expression by which we know what is the first expression gives me how the altitude or the satellite radius, orbital radius, it changes with time, and this one gives me how the period changes with time. Now, suppose we can measure, that is the period of a satellite completing one period. If you know that time, then we can calculate the what is the atmospheric density from this expression. So, basically rho will be equal to this dt by dt divided by this expansion 3 pi a C a by m. Now, another very important term, that is called the ballistic coefficient beta. This term is kg per meter square, it is defined by, this is the term. So, here what is m by a? M by a is the mass by area ratio, mass by area ratio. So, when suppose the mass by area ratio is very small for a particular value of the drag coefficients, then I will have a very low value of beta. So, low value of beta means there is the chance that the satellite will decay its orbit. So, this value, the ballistic coefficient will give an assessment about the how fast this satellite will, its orbit will decay. Similarly, higher value will give me that it is more stable. So, it is a measure of the relative effect of the drag force on a body. Now, another expression, a very approximate estimate of the satellite's lifetime L due to atmospheric drag can be computed from using this equation, where h is called the scale height and dA by dt already you know the rate of change of semi major axis, and L is the satellite lifetime, it is in second, and h is the atmospheric scale height. So, atmospheric scale height h is equal to k T by m g, that is already we have seen in our last sessions. So, but if you want to have a more accurate value of this satellite lifetime, then we need to consider when we do this calculation of this dA by dt. So, there you have to take into these changes of the atmospheric density as a function of altitude, then its latitude, longitude, time of delay and the solar activity. Now, another parameter also, it is called the thermal or energy accommodation coefficient. So, what happens, the drag coefficient of a body can be determined by evaluating the force that results by the interaction of the incident air particles with the surface of the body. How the surface interacts with the body, how the particles gets reflected, what is the type of reflection. Those factors also can be found, and that by using those things the drag coefficient can be determined. So, air particles that impact the surface are re-emitted with a velocity and a directional distribution dependent on their initial velocity. So, what is it means? Whenever a flux of this is the particles, neutral particles are striking the surface, they are re-emitted with the velocity as well as there is some directional distribution. Okay. So, they again and it also depends on the temperature of the surface and the surface properties such as roughness. So, these are the various parameters on which what is the re-emission and what is the reflection or the scattering, that will depend on these parameters. So, the interaction can be characterized by the thermal or energy accommodation coefficient, which is a measure of the amount of energy transferred between a molecule or atom and a surface defined by. So, this is the expression. So, what is here EI? EI is the incident energy of the atom or molecule, then ER is the reflected energy of the atom or molecule, ES is the energy of an atom or molecule with the temperature of the surface, alpha is the thermal accommodation coefficient. So, now if the atoms or molecules impact then leave the surface with the same energy, means when EI is equal to ER. So, this energy accommodation is 0, this means alpha is 0. So, when alpha is 0, it means that there is no energy transfer with the surface and the emission is specular. So, specular means it is so it is coming and it is going exactly. So, these are the called this type of reflections, these are called this is a specular reflection, specular reflection. I could not draw it, this should be parallel, this all the rays should be parallel, incident parallel and reflection also parallel. So, if the atoms or molecules impact and leave the surface with the temperature of the surface, that is when ER is equal to ES, the reflected and the whatever the temperature of the surface, if these two energy are the same, then the thermal accommodation coefficient is 1. In that case, you will have because this ER is equal to ES, so alpha value will be equal to 1. And in that case, this re-emission is this is like a diffusion. Diffusion means it is coming and it's so there is scattering in different directions. So, this is called the diffusion. So, these accommodation coefficients can be thought of as the measure of the reflected molecules that are emitted diffusively. So, now we will take a numerical example. So, this example says a 100 kg satellite is in a circular earth orbit at an altitude of 400 kilometer with an effective cross sectional area of 1 meter square. If the drag coefficient is 2.2, the scale height is 60 kilometer and the atmospheric density is 2.5 into 10 to the power minus 12 kg per meter cube, then you are asked to determine the rate of change of the period, and the second question is the rate of change of semi major axis, and the third question is make an estimate of its lifetime. So, it is given A is equal to 1 meter square, then the drag coefficient C D is equal to 2.2 and the scale height h is equal to 60 kilometer. Now, kilometer we have to convert it into meter. So, we will multiply it 60 into 1000 meter. Then the mass is given 100 kg, then the air density is rho is given by 2.5 into 10 to the power minus 12 kg per meter cube, and the altitude A is equal to. So, it is given from the surface of the earth. So, you need to add the radius of the earth. So, A will be equal to 400 plus the radius of earth is 6378 and then this units are in kilometers. So, you need to multiply by 1000, then it will be in meter. Then the mu which is given by the mass of earth multiplied by the gravitational constant g. So, this value is 3.96 into 10 to the power 14 kg per meter cube. So, if we now we are having all these inputs, now we have derived the formula for the change of the orbital period with time dt tau by dt is given by minus 3 pi rho a, then C d multiplied by a divided by m. So, if you substitute all these values, we can show this is equal to minus 3.51 into 10 to the power minus 6 second per second. So, why second per second? Because the period is also in time and you are calculating the change in time with respect to time. So, that is why the unit is second per second, and the change in the altitude or the orbital altitude, that is dA by dt with respect to time, I can calculate it to be minus 2.86 minus 3 meter per second using the formula which are given in the earlier slides. And we can calculate L is equal to, that is minus h by dA by dt. So, this is basically is equal to we will get something like if you substitute those values, you will get 20.8 into 10 to the power 6 second. So, this is equal to 5828 hours, which you can convert it into days. So, this is 243 days. So, if you do not do anything, the satellite will from its height, that is orbit height of 400 kilometers, it will get deorbited, it would be lost within 243 days. So, in the next class we will discuss the other effects of the neutral atmosphere. And especially we now discussed these are all the natural, that is the microscopic particles, and then we will go to the macroscopic particles. So, in this lecture we just try to describe you, that is these are called the neutral atmosphere. We have considered the microscopic, that is the atomic oxygen, or so these are the natural microscopic. So, in the next class we will be telling about the micrometeors or other the particles, how it is impacts and how the satellite behaves under those environment. Okay, thank you very much.